First stage, main engine ignition. Lift.
Okay, here's an introductory video just to look at what is remote sensing. It's an introduction to the undergraduate honours option in remote sensing of global change. Now, ultimately in this course we're looking at measuring properties of the Earth. And you'll find that the term remote sensing and Earth observation, sometimes they're used interchangeably, sometimes they're used in different ways. So this little video is just looking at what we mean by remote sensing in the context of this particular course. Now you'll find many different definitions of remote sensing. Here's one from Paul Curran in 1985. Remote sensing is the use of electromagnetic radiation sensors to record images of the environment which can be interpreted to yield useful information. Now I would actually argue this is not a very useful definition of remote sensing, and it's certainly not the one that we want to use for this course. Partly because we're not just looking at images, we're looking at data. So collecting sounding data of the atmosphere, for example, in terms of concentration or temperature of the atmosphere. It's not really imagery. So we're recording data of the environment. I would also scrub a bit at the end here in terms of being able to interpret it for useful information, because clearly we're only interested in sensors that record data that are going to be interpretable and useful. So it kind of is not worthwhile putting in the definition. And the other thing, although we will look very much at the use of electromagnetic radiation, that's certainly the most common. Electromagnetic radiation is not the only way in which we can do remote sensing or Earth observation, because we're going to use, or some of you might look in a bit more detail at things like gravity or magnetism. So you can cut this definition down to remote sensing is the use of sensors to record data of the environment, which is a bit of a sparse definition. It's a bit thinned down. So let's look in a little bit more detail about what we're going to mean by remote sensing in this particular course. Well, my definition is that remote sensing is the science of measuring or inferring the physical properties of an object or medium using a sensor that is at some distance from the object or medium. And generally we mean by some distance from the object or medium. It's not in direct contact with that object or the thing you're trying to measure. You're not putting a thermometer into the atmosphere to measure the temperature, but you're measuring it from some distance. Typically, the term is used to describe measurements of electromagnetic radiation. So things like light and microwaves and infrared. And that electromagnetic radiation is either scattered or it's emitted from the Earth's atmosphere or the surface. And we sense it, we make those measurements using instruments on aircraft or satellites, but also other kinds of platforms, which we'll talk about in a minute. A more general definition, although we're going to focus mostly on electromagnetic radiation, a more general definition would include measurements of acoustic waves. So in terms of sonar through the water bodies, whether that's lakes or the oceans. So you can use acoustic waves to measure properties at a distance. And also magnetic fields and gravity. These are also used in the context of certainly satellite measurements of the Earth, but also airborne measurements of the Earth's surface and subsurface. And I would also suggest that we would encompass, in the context of remote sensing, measurements of the other planets and their moons in the solar system using interplanetary probes. So not probes that actually land on the moon or go into the atmosphere of a planet, but are actually measuring them remotely by going, say, into orbit. So it's quite a general definition of remote sensing. The term Earth observation is also used very commonly now. It's in widespread use, but it's normally restricted to describing regional to global scale measurements from satellites. So looking at certainly whole countries or whole regions, whole continents, up to looking at the whole planet. However, more recently, you will come across the Group on Earth Observations, and we'll come across that in the context of this course later. And they've actually broadened the term. They're actually looking at the collection, processing, modelling and dissemination of data about the Earth system collected through in situ, airborne and space-based observations using satellites, buoys, seismometers and other devices. So in fact they are very broadly defining Earth observation as any kind of observation of the Earth's environment or the Earth system. A quick reminder, the electromagnetic spectrum is something you're going to have to become more and more familiar with. So if you're not familiar with it, study this diagram or go and look at some books that will help you get to grips or remind you of properties of the electromagnetic spectrum. The bit that we're all familiar with, of course, is the visible part of the spectrum, which is what your eyes are sensitive to and what you can see. But we also have into the longer wavelengths the reflected infrared, the thermal infrared, right up to the microwaves. And we will look at all of these wavelengths as means of measuring some kind of property of the Earth, either its atmosphere or the surface. At the shorter wavelengths, we can get into ultraviolet, the X-rays, and gamma rays. And although these are also types of remote sensing in each of these wavelength bands, we're not going to specifically look at them in any great detail. We might consider, or some of you might consider ultraviolet when we're looking at the atmospheric composition. But X-rays and gamma rays, much less so. So that's the spread of the electromagnetic spectrum. And in a separate video, I'll explain a bit more detail about the electromagnetic spectrum and the kinds of properties that you can infer from measuring the electromagnetic spectrum. Okay, fundamentals of a remote sensing system. In general, you're always going to have some kind of source of electromagnetic radiation. It's going to come from somewhere. Sometimes it comes from the object itself. Sometimes it comes from a secondary source such as the sun. Sometimes the radiation is you're actually generating yourself from your own platform to illuminate the surface, much like a flash camera. There's also some interaction with the Earth's surface going on, whether that's emission or reflection or scattering, so that sometimes the object you're looking at is the source of the radiation, and then you have emission. Sometimes the object you're looking at is just reflecting or scattering that radiation, or sometimes it's absorbing it. There's also a bit of there's always going to be interaction with the atmosphere. Even when you're looking at the atmosphere, there's always other atmosphere that's in between you and that bit of atmosphere that you're trying to measure. So that's something that has to be taken into account. And obviously there's a sensor, which is some means of measuring the actual signal that you're interested in. Okay, let's draw a little sketch here just to show you the main setup for a remote sensing system. And down the bottom here we're going to have some kind of target. Okay, we don't need to specify what that is at the moment. It could be just a physical object, it could be some vegetation, it could be the sea, land surface, it could be the atmosphere, it could be a parcel of atmosphere, it could be a cloud in the atmosphere. All the different kinds of things that we might want to measure. Now in the first instance, and when you look at the video or read the material on electromagnetic radiation, you'll find out the relationships to do with the fact that, well, if it's got a physical temperature T, it's actually going to emit some radiation. We don't have to go into the details of that here, but the idea is, first of all, the notion that, well, it could be emitting some radiation. Clearly what we need is then some kind of sensor, which traditionally you sort of draw as a little antenna system. Okay, this could be a satellite, could be a handheld thing, could be something on a tripod. Doesn't really matter at the moment. We're just looking schematically at the setup for remote sensing. And obviously this radiation that's emitted from the object can reach our sensing system and we'll make a measurement of the radiation that's being emitted. Now of course it's not as simple as that, because even if it is atmosphere that we're looking at, in between the sensor and the object that we're looking at there'll be some atmosphere. So this is just to represent the layer of atmosphere. So in any scenario where we're trying to measure the properties of this object down here, we need to consider not just the radiation that's emitted and the properties of that radiation, but we need to consider what's going to happen to it as it passes through the atmosphere. Okay, let's think of a different scenario. So it's not emitted radiation, but it's radiation that comes from somewhere like the sun, for example. So it's a secondary source of radiation. So we've got our sun up here. And the sun, of course, is a fantastic source of electromagnetic radiation. It leaves the sun, it passes through the atmosphere and reaches our object, which may be another block of the atmosphere. And then it may scatter this radiation, it may absorb it and re-emit it. There's a number of different things that it can do, which we'll look at in a different video in terms of how the radiation might interact with that object. But some of it may be scattered or reflected back through the atmosphere and be picked up by our sensor. Both this case and the case where you've got emission from the object we refer to as passive remote sensing. So it's passively sensing the radiation that is coming from this object, whether it's emitted or whether it's scattered or reflected. There's another kind of remote sensing which is referred to as active remote sensing. What active remote sensing does is actually it generates its own kind of radiation or signal. It's not always radiation because it can be passing through water, so seismic studies or sonar is actually transmitting a sound source. But if we just consider electromagnetic radiation, what we actually have is that in the first instance it's our actual platform that is sending out some radiation. So LiDAR and radar are two specific examples that transmit electromagnetic radiation at the object. It reaches the object and then of course is scattered or reflected back. And we ultimately measure it back at the sensor. So it's radiation that we've created ourselves. A typical analogy for this is if you just use a normal camera to take a picture, you're using passive remote sensing because you're measuring signals from it's just the general ambient light or the solar illumination or illumination from indoor lighting. If you use a flash camera or flash with your camera, you're actually generating your own illumination. And that's the difference between the passive and active sensing. Final scenario is actually measuring the transmitted electromagnetic radiation. So if we move or get rid of this object down the bottom here and instead add in a new object up here somewhere. This is usually going to happen with in the context of the atmosphere. That we may have a source, and it may be the sun or it may be a small star, but it will be some other kind of source that's behind it. That the signal actually comes and is transmitted through the object of interest, and we measure the signal that arrives at the instrument behind the object that we're interested in. And this is another form of remote sensing, another scenario whereby instead of looking at the scattering or reflecting properties of an object, we're looking at its transmission.
So let's consider different kinds of platforms, simply just to go through to make sure that you have some sense of the diversity in which remote sensing is actually used and actively employed to measure properties of the Earth's environment. Now you can go up the left hand side here. This is just sort of my vertical scale, so we're going from the ground surface up into outer space, or at least the orbit around the Earth. And we can start simply by saying that, well, remote sensing can kind of include effectively ground-based measurements. So in this case here on the top of this tripod is a little radiometer that's actually measuring properties of in this case the snow surface, the snow and ice. But there is a distance. The distance is only a couple of meters, but it is measuring the properties effectively remotely, just not very remotely. On the right here we've actually got an example where it's beneath the surface. It's actually underneath the water surface and looking at the reflectance of and the scattering of electromagnetic radiation from the surface beneath a depth of water. And these are all, strictly speaking, they are forms of remote sensing. It's just that the platform is not very remote. Very often this kind of platform is actually, or this kind of remote sensing is done in support of airborne or satellite sensing. So it's making some kind of ground measurements in a bit more detail to help understand what the more remote measurements are telling you. What the more remote measurements are telling you. We can go a little bit higher. You can put remote sensing instruments on top of cherry pickers, so we're getting up to 10-15 meters or so. Also on the top of cranes. A very common activity, or fairly common activity in terms of looking at forests and remote sensing of forests, is actually to have instruments that get up above the canopy. So it's still very much looking at detailed research into the electromagnetic properties of, say, a forest canopy, but it's still a kind of remote sensing. We can go a bit higher into airborne platforms, and airborne platforms can go from a few hundred meters up to 10 kilometers or more. So some of the larger instruments, this NASA instrument at the top, or NASA aircraft used to carry many different kinds of remote sensing instruments. Smaller aircraft, or even UAVs, unmanned aerial vehicles, or ultralights. The School of Geosciences, of course, has our EcoDemona, which is a small research aircraft that carries pods with instruments on it. So there's a wide variety of airborne instruments at different scales, heights, that can make measurements both of the surface, but also measuring properties of the atmosphere. Once you get into a few hundred kilometers, you're getting into what's called low Earth orbit. The space shuttle typically is in orbits of about 200 to 300 kilometers. It's not, because there's still a small amount of atmosphere there, it's not very good for long-term instruments to be in orbit, in a low Earth orbit, because the drag effectively slows it down, so it uses a lot of fuel to keep in orbit. But the space shuttle is only typically up for a few weeks at a time. The shuttle platform, of course, has carried a number of different remote sensing instruments in its time, both optical imaging cameras, just like large photographic cameras, and also radar instruments and atmospheric sounding instruments. Many hundreds to about 1,000 kilometers is a typical Earth observation orbit. So many, and probably most of the satellite that you will consider in this course will be in that kind of a range. Typically 800 kilometers is a very typical orbit for Earth observation instrumentation. When you get to very high orbits, so specifically up to about 36,000 kilometers, you're into what's called the geosynchronous orbit. And that means that a satellite takes approximately 24 hours to orbit the entire Earth. And of course the Earth beneath it is rotating on a timescale of 24 hours. So the satellite always appears to remain over the same point on the Earth's surface. And the meteorological satellites are mostly, or many of them are based on a network of geosynchronous orbits. If you go and look at the orbits tutorial or the orbits video, you'll see a bit more information about these different orbits and the impact it has on the coverage. So that was the different kinds of platforms. One question, I guess, for you is, why should you be interested in remote sensing? Well, it's a very interesting subject. It's a rather trivial answer to that question, but it is true, and you might find it simply an appealing subject to look at because it's a fascinating and interesting subject. Perhaps more importantly, for most of you, it's important that you know about remote sensing because it's increasingly a part of the earth science, or what you might call the culture of earth science, both in terms of the specialized science, so in terms of looking at climate change, current climate change, understanding environmental change, biodiversity, the range of possible things that you might look at in Earth system science will probably now all include remote sensing of some kind or another. Whether that's airborne or whether that's satellite-borne, of course, there'll be a mixture. And also just in the public domain, in terms of our perception of planet Earth and the changes on planet Earth's environment, Earth observation is increasingly a means of communicating that change. So it's important from that perspective as well. The reason, of course, that it's a fundamental part of Earth system science is that it provides unique information about planet Earth. It also provides unique information about the other planets. and that's something that some of you may pick up on your projects, but not something we will explicitly look at in the lectures. But it does provide unique information that you can't get in any other way, both about planet Earth and other planets, and so it's very important from that perspective. The other thing that you individually might be interested in, of course, is that you might want to use Earth observation or remote sensing data in your dissertation. And data is often a limiting factor in that, but also a key limiting factor is also understanding that data, understanding where the data comes from, understanding what it means, and how to interpret or to understand the significance of the data that you might be looking at. Why use satellite remote sensing? This course is very much focused around satellite remote sensing. So many of the other option courses available in this school look at satellite remote sensing at a slightly more detailed level, but we're going to focus really on regional and global scale monitoring. So of course satellite remote sensing is unique in respect of the fact that it does provide global monitoring. It provides the possibility to measure some properties of the Earth within 24 hours. So the entire global monitoring of, say, ozone in the upper atmosphere or sea surface temperature can be done within a day or two. It's an objective, consistent tool for environmental change, both in temporal and spatial dimensions. And of course what that effectively means is that you're using the same instrument potentially to measure all the properties around the globe and over a long period of time. So you don't have to worry about intercalibration of instruments across the planet, ground-based instruments. And it's objective in the sense that it's not based on an individual group or people that are making those measurements. In theory, the data is collected from the satellite and everybody is then free to analyse and interpret that data. It's also very important because it measures at a variety of scales, so you can measure locally and globally, but over large regions. And it's now providing certainly the largest archive of spatial digital data available. You just have to go to look at Google Earth to see just how much data is starting to be both collected and made available in the public domain. Very importantly is that satellite remote sensing provides measurements that are simply not possible by other means. There are some things, say, such as measuring the Earth radiation budget, which is simply not feasible to be measured from beneath the atmosphere. You have to get up and above the atmosphere before you can actually make sensible and meaningful measurements of the Earth radiation budget. And there are other things that we will look at in this course that are measurements that are difficult to make otherwise. And all of this can be done very quickly. I mentioned this scale of 24 hours. In fact, global coverage of the say cloud cover around the planet is updated every 15 minutes. So our measurement of planet Earth is increasingly becoming very timely and rapid and very extensive, both in the detail of the measurements that are being made and the range of different kinds of measurements that are being made. So that was an introduction to what is remote sensing, and to give you some feel for what it is we mean by remote sensing in this course.